Okay, page 13. We didn't get through any of this yesterday, right? We just did a little bit of the back page. Okay, so what I would like to do with these 6 problems is talk about what the first step is for each of these problems. Okay, because I think that's the hardest part with these general problems. Is no one what that first step is. If you figure out what that first step is, everything else kind of just follows a predictable procedure. Okay, so as a rule of thumb here, well, obviously if you see trig, a lot of times that's going to be a U substitution, but if you just see x's in the problem, variables in the problem, then we always want to consider our first option being expansion. Okay, can I just rely on expansion power rule to get me through the problem? If I can, then I want to go ahead and do that. But if I'm able to rule that option out, either because the degree is too high for me to expand out, or a square root or cube root is involved, that where I'm just unable to resolve using order of operations, then I'm going to look at U substitution. Okay, so take a look at number 1 here. Am I able to work my way through simply by relying on expansion power rule? Yes. Okay. So you saw this type of problem on the last quiz where you separate it into individual fractions. You brought that denominator up, and then you're able to clean everything up and rely on power rule. Okay. So this one we can expand in a sense, and then power rule. Okay. Now, take a look at the problems on the board there. I have integral of 3x minus 4 squared root x, and I also have 5 root x times x minus 5 squared. I meant to put this squared up here. Over 8 root x to the 5th. Now, we do see a bunch of parentheses in the problem, but none of the parentheses are messy enough or difficult enough where we can just expand our way through, right? This first one here, I can just take my time to expand that x minus 4 squared, distribute the 3 root x through, and then just rely on power rule, right? Everything is nicely separated. This one's a little bit more involved, but the same idea here. I can get the numerator expanded out and then separate with the denominator. So there's no need for U substitution for the first 2 methods. Now, if you look at the one below here, this one, the numerator looks fine, right? Expand this out, not an issue. But as soon as you introduce more than one term in the denominator that's separated by plus or minus, your power rule ability is out. So like even something as simple as 5 minus x in the denominator is too difficult for expansion to do. So denominator is okay for power rule, but only if it's one term. As soon as it gets down to more than one term, you know your expanding power rule options out. I just want to point those out. Okay, number 2. All we see are x's. So can I distribute my way through for number 2? No. Okay, so I'm stuck in this form. Power rule option is not going to be available to us. So now our second option is U substitution. So what's our U value? Yeah. Now I'm skipping some steps here. Normally we would rewrite that radical as parentheses to the 1/2, but you know, once you see that parentheses, we know it's 1 minus 3x squared. Okay, so I just want to talk about the first step for everyone before we go back. Okay, I think that's the most important part. Okay. Number 3. First option, can I expand my way through? This one I can. Okay, the parentheses have nothing that's preventing me from distributing. The power is not too high. I don't have it's not part of a root. The square root of x is just a single term. That's okay. I can just distribute that through. So this one I can expand and do power rule. whenever you see trig, usually that's an indication that, okay, I'm probably gonna have to rely on use substitution because I can't do power rule with trig. So what's our u value for number 4? 3x squared, right? 3x squared, that will handle the 5x, and we're left with integral of secant squared u, and that's going to end up with secant squared giving us tangent. Okay. Okay, number 5. Can I distribute my way through? Can I rely on power rule expansion? No. Okay, so I'm stuck in that form. Okay. What's our u value? 7 minus x. So if we look ahead a little bit, is the x going to go away on its own after we make our substitutions? So if I find the derivative of 7 minus x becomes -1, is that -1 going to help me with anything with this x squared? No. So this is one of those problems where, I mean, you're going down the right path, you're going through your substitution, but that x squared is not going to go away on its own. So we have to go through a little bit of a change of variable here. We have to make another set of substitution. Okay. So I definitely want to go through this in detail. This is the problem I think takes the longest to get through. Okay, but we'll practice with that step. Okay, we'll come back to this one for sure. Okay, number 6. Can I expand my way through? It's possible, but what? 3 is a little high, right? I mean, I could do it, but you know, if we have a faster method, then we want to approach it. So our u value here is 1 minus 2x squared. So anytime you see a definite integral with a bounds given to you, you want to ignore it, right? There's a problem that we have to first solve and take care of before the bounds have any sort of a say in this problem. So we go through your substitution. Is this going to work out nicely with that remaining x that's sitting out there? Yes, yeah, that derivative is -4x. That -4x will handle this x in the front. There's a leftover coefficient, but this is a relatively straightforward problem. We just have to deal with the bounds once we take the antiderivative. Okay, let me just give some highlights for each of the problems, and then we'll go back and look at the details. Okay, so number 14, sorry, page 14, number 7, 7 and 8. These are both procedures involving what? Okay, it's asking for the derivative of an integral. So if we pair those up, that's what theorem is that? It's like the second theorem, okay? So as a reminder, second theorem says if I'm pairing a derivative and integral notation on each other, then it's okay. Then we can plug the upper bound and lower bound directly into the expression. Okay. Normally, if it's I keep saying if it's a definite integral, we got to do the calculus first before the bounds come into play. But here we're pairing derivative integrals next to each other. There's a doing and undoing of a process. So we can just jump to the end. Okay, so rather than have to go through that full process and undoing that full process, we should have to plug the upper bound into the expression, multiply it by the upper bound's derivative. And then if the lower bound is also a variable, we do the same thing as we did with the upper bound, f of q of x times q prime with a minus in between. Okay, so we'll go through those two. For 9 and 10, okay, we're not going to go through any calculus procedure per se, what's the strategy here? Okay. Yeah, we graph it. What two shapes are we going to come out with? Two triangles, and we just figure out the dimensions of those two triangles, and we add those two areas up. 1/2 base times height, 1/2 base times height. Okay, so we did number 9, right? And I'll go over number 10 with you. Number 11. Okay, it says starting with acceleration and the position and the velocity order pairs given, find a specific function of v of t. So how do I get from acceleration up to velocity? Take the antiderivative, I'll go through power rule, a plus c will show up, and then I can use the order pair to help me solve for c. And then once I'm at the velocity function, how can I make my way up to the position function? Take another antiderivative, another set of power rule, another plus c will show up, and then use the order pair here to help you solve for that c value. Okay. Let's look at number 12. Okay, I want to do number 12 in full, and then we'll go back and revisit the rest of the problems here. So number 12 says the graph below consists of a semicircle, triangle, and squares. I'll give you a formula for the semicircle. Area is 1/2 pi r squared. I'll provide that on the test. So let me highlight the graph. Okay, so here's the function. The function f is here. So there's the function f. Find the average value of the graph on the interval from -2 to 5. So average value, that's average value theorem. Let's go ahead and recall that. What's the average value theorem? 1 over b minus a. That's the width component. And then now I'm going to build the area component. Sorry, width component. Integral from a to b of f of x. Okay. All right, so what are our a and b values? Yeah, that's a left and right bound. So I'll go ahead and update my formula with the a and b values. 5 minus -2. Five minus -2 becomes what? 7. So 1/7. Okay. So how is the graph going to help us with this portion? Well, if we had a function in front of us, we would take the antiderivative. But here they give us the graph, so we just have to focus on figuring out the area. However, it's area related, right? Anything that's below the x-axis, we have to adjust it and make it what? Make it negative. Okay. So let's just spend the time to find the area of each of these regions here. I got a triangle, I have a square, a triangle, a semicircle, a triangle, and a square. So all this added together with the positive and negatives will represent this region here, or this portion of our problem. Okay. So one shape at a time here. 1/2 base times height. 1/2 1 times 1. The square is 1 times width times height, which is 1. Triangle there. Another 1/2 base times height. 1/2 1 times 1 is 1/2. Now we got to convert this to a minus, right? 1/2 pi r squared. What's the radius of this semicircle? 1. Yeah. So 1/2 pi 1 squared. Back to above the x-axis, so plus 1/2 plus 1. Okay, clean up as much as we can here. 1 plus 1 is 2. Plus 1/2 plus 1/2 is 3. So I have 3 plus 1/2, which is 3.5. Minus 1/2 pi times 1 squared. That's, I can say minus 1/2 pi or minus pi over 2. So there we have it. This is representing the area or the definite integral of this region. Okay, everybody okay with what we've done so far? Okay, so now we can find the average value, f of c. I got the 1/7 sitting on here, and then the 3.5 minus pi over 2. Okay, you can distribute through. I mean, this you basically have a, if you have a numeric representation of the answer, that's good enough. Okay. All right. All right, let's go back. I have the key attached, so I'm going to just focus on the ones that I feel are more involved, right? I think one, you guys should know how to do this. The key is attached. You demonstrated your ability to do these types of problems on the quiz. Use substitution where things cancel out is clean. The expansion power rule is not bad. Use substitution for trigs, not bad. I want to go over numbers 5 and 6. These are a bit more time intensive. So if we have time, we can always go back and do the easier ones. Okay, so let's go through the steps for 5. Okay, so we predicted that we're going to run into a bit of a roadblock, even though we're going down the right path. The x's does not go away for us because the degree of the u value is not high enough to cancel out that x squared. So we know we got to deal with that x. Either the x's cancels out, which we can't make that happen, but we're able to find a replacement for x in terms of u, right? So what's available for us to get that x replaced? You know, this is a signed equation between u and x. Right? So x equals 7 minus u. So we have to go through this process here, make that substitution, and that will get us one step closer towards expanding everything out and relying on power rule. Yeah, I want to make sure that, again, we can't do this. I see some students in the past, they would look at this and say, well, I'm going to forge ahead and still go through power rule. And they start doing power rule for each of the variables. Okay. It doesn't quite work as easily as this. Okay. We can't separate the x from the u, especially if there's multiplication in between. So we can't do this. Okay. We can't just treat them independently of each other. Okay. So take the integral. 7 minus u squared. Right, so at least everything's in terms of u, in terms of one variable, which is good, but we still can't do power rule, right? We still have all these, we have some parentheses to resolve. We have to distribute that u to the 1/2 through. So Step by step, I'm gonna try to get there. Make sure you don't distribute the u to the 1/2 through first. You got to expand, right? Exponent takes priority over multiplication. Now we're ready for power rule. So notice that I'm hanging on to all these integral du notation because I haven't done anything with calculus yet. I'm just trying to get it to the point where I'm ready for my power rule. So once I'm here, I can apply power rule. Once I apply power rule, then these notations can drop out and I can replace with the plus c. Let's apply power rule here. Flip all those fractions up. Combine all these coefficients, and then what's one step that we have to go beyond this? What's next after that? Yeah, bring the original variable back. Okay, so your answer is never going to just be in terms of u. You gotta, if you go through your substitution, that's just a temporary variable. You got to bring back your x. Okay. Number 6. Sorry, from 1 to 2. Okay, balance is the last thing we touch. Expanding is possible, but not efficient. So our next option is use substitution. We have a nice u value that we can use there. right? Did the x's go away here? Yes, x's cancel out. What can we push out in the front? -1/4. Nice power rule. Okay, so now we're sitting at the antiderivative. Now we don't do a plus c because now we're going to involve the bounds. Just be careful here. We don't want to involve this antiderivative with the 1 and 2 because why? What's the issue? Yeah, the variables are not the same, right? This is in terms of u, but the bounds are in terms of what? In terms of x. Okay, so either we get the x's, these both be x's, or both in terms of u, but we can't have one x and the other being u. Okay, so we have two methods here. The first method, so call this method 1. I think most students prefer this. Just bring the u back in terms of x and then use the original bounds. Between 1 and 2. Okay. Now, you're not required to simplify and clean up, especially without a calculator. So as long as you're able to represent your answer as a numeric form, simplifying it is not required. So that's one method, getting everything in terms of x, and then once the variables match, you can go through your process. The second method is converting the bounds, which will allow you to use that negative u to the 4th over 16. So my original lower bound was x equals 1. My conversion is 1 minus 2x squared. Okay, plug 1 in for x, I can solve for u. Okay, again, if you want to go through this method, just keep in mind that if you start with a lower bound, you're going to keep it as a lower bound. If you start with the upper bound, you'll keep it as upper bound. Even though it feels like it's swapping places, the -7 is a lower value, but things will work itself out the way it's supposed to. If you really want to change the bounds, you can, but if you flip the bounds, you got to change the sign. So I should usually leave whatever I see there and not have to worry about it. Same results. Sorry, 16, not 4.
it be positive, the negative times negative one of the
The issue is that we don't deal with these two negatives because we got to resolve this first. What's negative 1 to the 4th? Just 1, right? So this becomes a positive, and so that negative stays. Okay, next page. Find the derivative of this integral. So know that we know that we're pairing a derivative with an integral. We know there's a second theorem. Okay, here's the formula that we're applying here. Upper bound into the expression multiplied by the upper bound's derivative minus, you got to do the same process for the lower bound because that's also a variable. So f of q of x minus q prime. So f of p of x just means replacing this any original t variable with the upper bound expression. Times p prime. P prime is the derivative of square root of x. This is really x to the 1/2. Go through power rule. 1/2 x to the 1/2 becomes 1/2 x to the negative 1/2. Minus big bracket, make big parentheses. Same process with the lower bound into the expression. Times the lower bound's derivative. Okay, so I'm just do some cleanup here. Oh, I messed up. Sorry, guys. I copied the problem wrong. Square root here. So sorry, these don't combine as cleanly as I thought. Okay, let's try number 8. All right, what do you notice about number 8? How many variables do we have? Only one, so only have to worry about just f of p of x, not have to worry about f of q of x, but do you see anything out of order? Yeah, we prefer that 3x squared to be up top. That way we can just rely on the rule and just plug in the upper bound and not worry about the lower bound. So that means I have to do what? Flip the bounds and change the expression, put a what in front? Negative. So now it becomes more straightforward. Just the upper bound is involved, the lower bound is a constant, that will just drop out to be a 0, so don't need to worry about the constant. I think number 11 is pretty straightforward. You demonstrated that ability on the quiz. Find the antiderivative twice. Each time will produce a plus c, and use the order pair to solve for that c value. I want to do a, I did not put this on the sheet here, but I want to do a trig definite integral problem with use substitution. So you can find room on a separate sheet. Okay, try this one here. I did this in the help session this morning. I think it's good to go over this one here. Okay, so first thing is recognizing that we don't deal with the bounds, right? The bounds is not going to play a role until later. So treating it like as if I don't see the bounds is a good way to begin. Now, do we have a single rule that can handle what we see in front of us? We only have 7 trig. Sorry, we only have 6 trig integrals, and none of them look like exactly like this one, right? We have integral for sine, we have integral for cosine, but we don't have one for sine squared cosine. So we immediately know this is not going to be able to be solved just by relying on the rules. We got to go through use substitution to create a different version of this problem. Okay, so let's get some parentheses to show up, or at least one set to show up. What's our u value? Sine x. Okay. And that sine x will work nicely with that cosine, because what's the derivative of sine? Cosine. So we know that things are pairing up pretty nicely. We're expecting the x's to drop out for us. So u equals sine of x, du dx equals cosine. Solve for dx, dx cosine equals du. We'll cross multiply first. Solve for dx, dx equals du over cosine x. And we make our initial substitutions back into our problem, right? We keep the square, we keep the cosine, but we replace the sine with u, replace the dx with du over cosine. Okay, so after that substitution, we get integral of u squared cosine x du times du over cosine x. Do the x's go away? Yes. Okay, so cosine x drops out. There's a 1 in the numerator, 1 in the denominator. So now we're left with a relatively clean power rule problem. U squared du. What does that become? U to the third, right? U squared becomes u cubed over 3. Do we put a plus C here? Okay, there's a bounds involved, so we have to, now we can think about the bounds. Can I rely on the negative pi over 3 and pi over 6 for this u cubed over 3? What's the issue? Different variable, right? So I want to keep reminding us of that because I keep seeing students wanting to match or mix and match between variables. So this is in terms of x, this is in terms of u. So either we get both in terms of x or both in terms of u, but we can't have one being x, the other being u. So the first method, I'm just going to continue with this antiderivative, bring this back in terms of x, and that way I can rely on the original bounds. So u gets replaced with sine x quantity cubed over 3. So now my antiderivative is in terms of x. My bounds are also in terms of x. So now I can plug in. So upper bound minus lower bound. Now, if this was an algebraic problem, you would be able to leave your answer like this and get full credit. Okay, but this is a trig problem, so we have to resolve these trig values before we can leave it alone. Okay, so that's a big distinction on the AP exam as well. It feels like it's the same thing as just plugging the value in and leaving it, but this requires an additional step. We got to resolve those these trig values. So sine of pi over 6, you think about your unit circle value, that's 1/2. Sine of negative pi over 3, we don't recognize a radian measure, you can add 2 pi to it or subtract 2 pi from it in order to get it into that unit circle or that between 0 and 2 pi. So sine of pi over 3, that's equivalent or similar to sine of pi over 3, but it's in the fourth quadrant, so we know sine is negative, so negative root 3 over 2. It ends up giving us a messy fraction, but I'll accept a messy answer, same as the AP exam, but if you want to keep going, you'll get all the way down to 1/24 plus 3 root 3 over 24 to reduce things even further and make it root 3 over 8. But you know, once you get it down to a numeric value, any variation is fine. Okay, that's the first option. The second option is leaving this in terms of u cubed over 3, and then changing the bounds to be in terms of u, and then going through that process. Okay. So let me show you that method. Okay, convert the bounds. Take the negative pi over 3 lower bound, push it through the u equals sine of x equation, and then get that updated lower bound in terms of u. Take the upper bound, that's in terms of x, push it through the equation, and get that upper bound in terms of u. And then you can use that u cubed over 3, evaluate between 1/2 and negative root 3 over 2, and you get the same result. All right, you can choose to do either way on it. That's, I'm not going to say do it this way and do it the other way. Guys, let me squeeze in number 10 here. This is the drawing the graph and figuring out where the two triangles are, dimensions of the two triangles, and adding up the two triangles. Okay, so absolute value of x minus 4. Where's that vertex going to be located? At 4. So I'm going to extend from -2 all the way to 7. Okay. Should be able to draw your two triangles. Now, if I can find the y values at these endpoints, I'm able to find height as well. Okay, so if I insert -2 into this absolute value function, I can get that y value. What's -2 minus 4? -6. The absolute value of -6 is 6. So the order pair is -2, 6. Look at that y value. That y value is the height of your first triangle. Second triangle, plug 7 into the function. 7 minus 4 is 3. Absolute value of 3 is still 3. And order pair 7, 3, but the y value is that height. Okay. So we're not going to have to do anything with power rule or splitting anything up. We just draw the picture and then just understand that integral is the area. So we just find the dimensions of those two triangles. What's the width of this first triangle? 6. The height is also 6. Second triangle, width of 3, height of 3. And we do 1/2 base times height for both triangles. So 36 over 2 plus 9 over 2 is 45 over 2. Okay, I feel like we've gone over all the big items that I want to. I know I didn't quite go over the entire worksheet, but I think I hit all the ones that I wanted to hit. Tomorrow morning help session. If you want to work through the morning review ahead of time, I think that would be a great idea. That way, if you have any questions, you can come in with those questions tomorrow morning. Okay. All right, come up and get your phones.
Can we go over that like everything is gonna be?
We did, yeah. I think I left this out, but you know the concept.
Yeah.
And then here. Let's do it. Guys, I didn't go over even and odd functions today, but I'll go over that tomorrow in the house session or
Yeah.